Welcome to Fresh Thinking. If you've ever watched clips of the Excel World Championship, it looks like esports for spreadsheets. People flying through formulas, keyboard shortcuts, and data problems at a ridiculous speed. But here's what I love about it. It's not just Excel tricks. It's a reminder that a spreadsheet can be a serious thinking tool. Today, we're taking the mindset into a very different arena, learning geostatistics from first principles using Excel as the lab bench. I'm Susan Havlin, Managing Consultant for Snowden Optiro. This episode is for geologists, resource modelers, and anyone who wants to understand geostatistics beyond click the Kriging button, which I'm yet to find that button. The goal isn't to replace specialist software. The goal is to see how geostatistic works step by step so the algorithms feel inevitable rather than mysterious. I'm joined by Gregory Zhang.
Thanks, Susan. Just on that Microsoft World Excel Championship. So Excel isn't just like back office. So it's now a legit esports stage with the streamed finals, the prize money, and the global audience. So that game pits competitors, against the rapid fire problem solving cases where the anything Excel goes, X lookups, ifs, dynamic array, Power Query, or even VBA. So I'm a big believer that if you can build the core workflow in Excel, at least on a very small example, then you have that intuition, and then you can carry that in any software package you use later.
Great. So, the obvious question I have to ask is why Excel?
Right. So because geostatistics itself is a chain of small decisions and calculations. So, for example, what data goes in, what doesn't, and how you treat the domains, what pairs you would include, what lag distance you choose, and how you fit the variogram, how you solve the Kriging weights, how you validate the outcomes. Those are the examples or the let's say the typical workflows we do, or most of the resource geologists do. And the Excel enforces the transparency. You can point to a cell and saying, look, this number comes from this and that. And that's very powerful for learning. And yeah.
Great. So you're not saying let's scrap everything and just do it in Excel, but this is a good starting point to make you understand what you're actually doing in these
Exactly.
other software programs.
Exactly.
So it maps to the daily reality of geology. A lot of quick checks, so QAQC, compositing, summaries. And does this make sense? Analysis lives in spreadsheets.
Exactly. So Excel is where the habits form, whether it's good ones or the bad ones. And learning geostatistics in Excel tends to improve both your understanding and your everyday data discipline. So let me ask you this. Do you use Excel like as part of your daily workflow?
Oh, yeah. I have at least like 10 Excel spreadsheets open at a time.
Yeah.
I wouldn't say I do my variography in it, but Excel is one of the tools that I use all the time.
That's the point. Yeah.
So talking about variograms, before we even say the word variogram, what are the spreadsheet advantages that matter most for geologists doing analysis day to day?
So I would say three things. The first is auditability, that someone else, whoever is going to take over your project or review your project, it will be very easy for them to follow your logic, without mind reading. And then the repeatability. For example, you could apply this workflow or the logic easily to other projects with the new data. And then the third, defensible summaries, where once you get the domain level descriptive stats and or outlier checks, top cutting or sampling support or visuals that tell the truth. So if you build those, you're already thinking like a geostatistician, and you are defining data quality, uncertainty sources, and the structure you trust.
All right, so let's do the learning path. If someone wants just statistics from first principles in Excel, What do they build?
So I would start with a clean, explicit data set. So make your data table boring in a good way that you only kept the necessary information, sample ID, XYZ coordinates, domain coding, and grades, or optionally, secondary variables, whether it's grade variable or the lithology, and then do the basic checks and see if there's any missing values, if there's any duplicate data, there's any impossible coordinates, because you've got to keep all the coordinate system consistent, or the domain mismatches, or the histograms and summary stats by domaining, and then the quick plots, for example, the trend plot, where we use to check the stationarity or anything that can help us to find out the potential issues at the early stage.
Great. I mean, I personally like it for pre and post compositing to make sure you're not losing any metal in your compositing stage, because that's pretty easy to do.
Exactly.
What I'm hearing, the first lesson is geostatistics doesn't rescue messy inputs; it actually just magnifies them.
Exactly.
So what's the first geostats looking sheet you make?
So let's say we're going through this process of using the Kriging, whether it's ordinary Kriging or simple Kriging, then the core engine is variogram modeling. So variogram modeling that measures grade continuity. And then to do that variogram modeling, the first step is we need to build up this pair table. That means we need to, by defining certain direction distance, we need to find all the pairs within that distance and direction, and then build up those pair table, then calculate the Euclidean distance, and then we're gonna we're gonna create this distance matrix. Then we will use that matrix to fit in whatever the variogram model we define, whether it's spherical, Gaussian, or exponential. Once we build up this data table or the pair table, then we can fit in this Euclidean distance into the variogram models and calculate the variogram or the covariance. And then that's the core part of this sample weight calculation. Then we can calculate the matrix, to get the sample weight, and then to get the estimated grade, that's simply weighted average. After we calculate the distance, then we can calculate the grade difference. So the grade difference, this one table gonna teaches the core idea that spatial continuity is measured through how difference behaves as the distance changes.
So then we get to semi-variograms.
Yes, that's right. So in Excel, what we do is we will find the grade difference, square that up, and divided by all the number of pairs we can find, and sum all the um, differences, squared differences. So that's the variogram value we will calculate for this direction and this distance. So after that, we would calculate that for all the distance and all the directions. Then we will plot it up. And that's the relationship between the distance and the grade variation.
Yeah. So then the learning happens when you change the rules. So like the lag width or the maximum different distances, or you change to a different domain.
Exactly. So you see how the choices will shape or infect the variogram, and then Excel makes that sensitivity obvious. And because you're not hiding anything behind the dialog box.
Great. So now to the big one, Kriging.
Kriging is a system of equations or the matrices. Excel is actually a great place to see that. And from a small number of samples, say couple, less than 20, what you can do is you can calculate this covariance matrix between the sample pairs, and then calculate the covariances between the sample and the point, which is going to be estimated. And then we can inverse that covariance matrix between the samples and multiply that with sample to point matrices. Then we can get the sample weights. Once we got that, then we can choose a weighted average, but also we can calculate the Kriging variance. So even if you don't go fully industrial, because this is a small data set, but still it can demonstrate a lot of very useful ideas when we talk about Kriging. For example, when the samples get close to the point and get far away from the point, how the sample weight is going to change, and then how the clustered sample is gonna work, and how the Kriging system deal with this clustered data, and how the nugget affects the smoothness, and why the variogram model controls everything fundamentally.
And so this is where Excel really shines for the first principles. So you can show the matrix, the weights, and the contributions. So there's no magic. It's all right in front of you.
Exactly. And not just ordinary Kriging, simple Kriging, or this logic applies to more advanced methods, including co-Kriging, multiple indicator Kriging, sequential Gaussian simulation, sequential indicator simulation. Again, not saying you can run the real life projects in the Excel spreadsheet, which no one does really, but you can expect it to be done as fast as commercial software if you just constrain that within a small data set. And building the algorithm from first principles in Excel can assure that you know it enough to call yourself a resource geologist.
So what you're saying is this is a good initial tool to make you understand what packages like Supervisor are doing in the
Exactly.
background.
Exactly, exactly. And also can be used as a tool to check if those commercial softwares are doing the right thing or not.
Yeah.
Yeah.
So finally, how do we keep ourselves honest?
So build very simple validation routines, including source plots, summary statistics comparison, or we call that whole of domain comparison, then tonnage grade reporting. So again, all of those can be done in Excel in more than one way, and in the reality, we also do that for the real life projects as long as you can streamline this process. And I know a lot of mining companies nowadays still use a spreadsheet as their main reconciliation system. It's probably not the best practice at 2025, but with enough clarity and construction, it worked for a lot of projects in the past. And I'm sure it can still work once designed properly from the proper level of complexity of the reconciliation process.
Yeah. So I guess we can also use the tool to learn the machine learning algorithms as well.
Absolutely. So some machine learning algorithms are not complicated. For example, the linear regression, so which we do that all the time. It's just we probably didn't know that's also one of the machine learning
Yeah.
techniques. And then for the complicated ones, for example, the random forest, self-organizing map, convolutional neural networks, it's also possible to write a small demo in Excel. So Excel isn't just for tables. It can be a great learning sandbox to see how machine learning ideas work under the hood. So you won't ship a mind scale model from Excel, but you can prototype the mechanics and build the intuition.
Great. So if the Excel World Championships is about mastery under pressure, the lesson for us is simpler. So Excel can be a clear step-by-step environment for thinking, especially when you want to learn geostatistics from first principles. So you can go from clean data, pairs, experimental variograms, model fitting, Kriging systems, validation, and actually understanding what each choice does.
Yeah, and once you've built it once in a transparent way, every geostat software workflow becomes easier to trust or easier to use or even critic.
Yeah. If you want a structured learning path that supports this style of work, Snowden Optiro runs training including essential Excel for geologists, advanced Excel courses to demystify the traditional linear and non-linear estimation methods and the common machine learning methods.
Yeah, the Excel World Champion, ship cases are deliberately non-domain, so it's a fair fight. But our work or your work isn't. So during that trainings, we would keep the competitive energy but swap in your context. So think production reports, reconciliations, geochem plots, analyze the correlation, and executive-ready visuals.
And you don't need to do it as fast as the World Championships.
That's a good point.
Well, thanks, Greg. This has been a really interesting topic. Thank you for coming along.
Thank you.
If you'd like to listen to more of our Fresh Thinking by Snowden Optiro podcasts, you'll find them for free on our website, Spotify, Apple Podcasts, Google Podcasts, and most other podcast platforms.